Welcome, everybody. Thank you for being here for today's session, Practical Istio. My name is Andrew Shu. I'm an engineering manager at Docker, and I'll be your MC for today. We have here joining us from all the way from San Francisco, Zach Butcher, founding software engineer at Tetrate. And fun fact about him, he's an avid bicyclist. He's got the scars to prove it. He's got 9 stitches in his leg right now.
Yeah. That is a statement of fact.
Very tough guy, very tough guy. Chick stick scars. Can I say that? I can say that with air quotes. He's going to be discussing the ways that Istio has been used to solve practical organizational challenges. Please give him a warm welcome.
Thanks for making it out to the talk today. Thanks for having me. So before we dive in, I want to kind of poll the crowd a little bit to see where we're at so I can tailor the presentation just a bit. So who here has heard of a service mesh before? All right, cool. Almost everybody. Great. Who here has heard of Istio specifically before? Excellent. Who has used Istio before? For real, in production, or just testing? Excellent. Great, that's awesome. That's way more than I thought. That's phenomenal. So for this talk, I will spend just a little bit of time at the beginning introducing the basic architecture just so that we're all on the same page. I'm not spending a lot of time on that. So if this is, for those of you that are not familiar with Istio already, I would recommend that there are a couple other talks that you can go see, including I gave a talk with Lin Sun last year at DockerCon that the video is available for. That's a better introduction to Istio. In this talk, we're gonna move past that and hopefully get into some more interesting things. We'll spend most of the talk in a demo, and at the end, we should have plenty of time to ask questions and to discuss. So with that, let's do a real quick whirlwind tour of Istio itself. This is the simplest example of our problem. I have 2 services and they want to call each other. A wants to call B. The way that Istio works and the way that service meshes in general are built to work is that we deploy a sidecar beside the application. This would be in the same trust domain as the application itself. That's actually a pretty important feature, right? So in Kubernetes, this would mean that the sidecar's in the pod. If you're, for example, trying to run in a VM, this would mean that the sidecar is in the VM beside your application. Once we have those proxies beside our application, we now need to configure them. We need to actually make them do things. And this is what the control plane is for. The first piece of the control plane that I want to introduce is the piece called galley. And it is responsible for distributing your configuration to the other Istio components. So when you author a virtual service or you write some Istio configuration, that'll go to Galley, and Galley will push it to Pilot or to Mixer or to Citadel, to the appropriate piece. Pilot is responsible for actually programming the sidecars. So Envoy is the sidecar of choice for Istio. The reason for that is because it's a highly configurable dynamic proxy whose behavior can be changed at runtime with APIs. Unlike the previous generation of proxies that we used that typically required a restart of the proxy to apply new configuration, we can reprogram Envoy on the fly dynamically with APIs. And Pilot is the piece that's responsible for doing that. Pilot is also the piece that is responsible for going to all the service registries that exist in your system and understanding the topology of your deployment. Mixer is the next piece of the control plane to talk about, and it's a little bit special because half the time it's kind of a halfway piece between the control plane and the data plane. One way to think about Mixer is that it's the slow path for the data plane. If you're used to switches which have a fast and a slow path, right? When a request comes in, Envoy is going to intercept that request, and it's going to ask Mixer whether that request is allowed or not. Mixer is going to render a policy verdict. Envoy will enforce that policy verdict and cache it. On the other hand, and that happens in the request context, so in the request path, right? So a request comes into a proxy, Envoy is going to hold up the request until Mixer gives a yes or a no, and then it'll forward the request on. On the other side of the request, asynchronously and out of band, after Envoy has finished processing it, it'll take raw metadata about the request, and it'll push it into Mixer. And this is the piece, this is where we generate telemetry about the deployment. Since a lot of people in the room have looked at Istio, you've probably heard that Mixer is a giant CPU hog, right? It's a huge resource hog. The reason for that is because it turns out it takes CPU power to turn data into information, right? And that's really what Mixer is doing when we're producing telemetry. We're taking a bunch of raw data, we're crunching it, we're making something valuable out of it. The final piece of the control plane is Citadel. And this is the piece that's responsible for identity in the system. So I mentioned earlier that proxy is in that Envoy, that sidecar, is in the same trust domain as your application. The reason that is important is because Citadel here is going to assign an identity to your application. And we're going to use that identity at runtime when we establish a connection to another service so that we can apply policy. Right? I want to be able to say, the front end service can talk to the back end service, but the front end cannot talk to the database. I would like to be able to author that style policy around which services are allowed to communicate. And if we're going to have authorization like that, then first we need an identity that we can authenticate. Citadel is responsible for issuing identities to the system, to all the workloads in the system that we can authenticate and that we can use when we establish a connection to another service. Those identities are a SPIFFE certificate, and that manifests as an X509 certificate that we'll actually use to encrypt the channel when we go to establish communication, right? So we'll do mutual TLS between two services using the SPIFFE identity so that on both sides there's an authenticated principal. That is what SPIFFE gives you. SPIFFE says, if you construct a cert this way, and you do PKI validation on that cert, and you do one more extra validation step, which Envoy implements, then when you validate a connection with a SPIFFE identity, that identity is authenticated. And then we can use that to apply policy around which services can communicate. Together, we call these bottom pieces the control plane. We call envoys the data plane because they're actually handling the bits and the bytes of your application. So we'll walk real quick through a request flow, right? So we have our A wants to call B. That'll get intercepted locally by Envoy. There are a bunch of different mechanisms that we can use to perform this interception. That can be with IP tables. That's the way that we've most typically seen it. Cilium has contributed BPF-based implementation, which is nice. It gives you a lot of efficiency wins over using an IP tables-based interception mechanism. But you could even do things like update your application to talk directly to the proxy over localhost or over a Unix domain socket if you want it to be more invasive. But by default, Istio tries to be transparent. We don't want you to have to change your application, so we use IP tables to capture traffic. Envoy is going to inspect that request and make a load balancing decision locally at the client site. Based on the protocol, how it does that is different. If we're in HTTP, we're going to look at the host header. If we're in TCP, I'm going to look at the IP address that you're trying to talk to, and we're going to assume that it's a VIP, right? If it's just some TLS connection, I'll look at the SNI, the server name indicator on the request. And we can use that information to make an application level routing decision or a load balancing decision around where that request goes. So A's sidecar caught the request, looks at it, it says, okay, this is going to B. It picks a specific instance of B to send the request to. Pilot ahead of time pushed all that data to Envoy so that it has the information to make that decision locally. When Envoy receives that request on the other side, it's going to go ask Mixer, do I let it through or do I deny it? We assume that we let it through, in which case Envoy is going to forward that into the application. The application is going to do whatever work needs to be done to handle that request and to assemble a response. Envoy is going to send that response back. The Envoy on the other side will take that and hand it back into the application. And asynchronously and out of band, both Envoys will report back to Mixer. This is a little bit of a lie. This has actually changed recently. So in current versions of Istio 1.1 and newer, we actually only have one of the sides that reports. Right? So we only report server side rather than reporting both sides today. But you could go turn on both sides if you wanted to be able to diff the metrics between the two. And that can tell you some instructive things around network latency, around perceived availability of client versus server. So in summary, this is our architecture. We have services that are deployed beside a proxy. We have a control plane that programs them. That control plane is composed of 4 key components: Galley for config distribution, Pilot for programming envoys, Mixer for applying policy and generating telemetry, and Citadel for issuing identities. And again, we could spend all day talking about just the features. So this is a very concise summary. It provides traffic management, the ability to do fine-grained traffic control, the ability to say that 1% of traffic goes to this particular instance or that one, or match on headers, other request features. The ability to do east-west traffic without intermediate load balancers. You don't need middle proxies. We can make load balancing decisions client-side. You can actually have more efficient network topologies with fewer hops because of client-side load balancing. We can have improved resiliency between applications by automatic retries, circuit breaking, outlier detection, and other things of that nature. We can start to visualize what's happening in our deployment. This is one of the single biggest reasons that people start to adopt a service mesh in general, and Istio specifically, is visibility. And finally, we can start to provide some security in the form of identity, encryption in transit, and policy around which services can communicate. And maybe the biggest, most important feature is that we can do this consistently across the entire fleet, regardless of the language that the application is written in, regardless of as long as it's communicating over the network, we can apply consistent policy, get consistent visibility, and have consistent traffic behavior. This is huge. This is the single biggest benefit of the mesh. It is pulling these disparate things across all the applications together into one central control point. This means that you can have a small team of experts that start to take on the complexity of metric log collection, metric generation. You can have a small team that starts to take on the complexity of encryption in transit and service identity. You can have a small team that enables everybody, all the application owners, to write resiliency configuration for their services. You can focus the pain of these really complex topics into a small team of experts rather than amortizing that pain across all of your developers. And amortize is probably the wrong word there, because that implies that it's cheaper when we spread it across all of our developers. In fact, it's the exact opposite. Because I have to spread it across all my developers, it's more expensive in aggregate than if I can focus that into the group of a small, into the hands of a small group. Whew, all right, so that is Istio. That was, I lost my time, so we don't know how fast that was, but that was Istio in a whirlwind. So the first practical use case that I want to talk about is cross-cluster load balancing. I was actually pretty excited. I don't know how many people went to the last KubeCon. I was pretty excited at the number of talks there about cross-cluster communication. Because what that tells me is that people are starting to seriously adopt the technology. Because when you have one cluster, it's a toy, right? When you have multiple, you're starting to get into real production scenarios with real problems and with real failure domains and the ability to actually run something reliably, right? One site, you're gonna have issues. The fact that lots of people are starting to talk about pain around multiple clusters is exciting because it means that people are starting to use Kubernetes in real scenarios where they actually have to care about availability, where they have to care about latency, things like that. So in that context, I want to talk about a particular organization that I got to work with. They, as part of a merger and acquisition, they had to take their application, which was deployed in one site, and they had to go and make sure that they had redundancy, right? So the company that was buying them needed more reliability than the company had today. They were fortunately already using hosted databases, so that takes away a large part of the pain here. And so all we're left with is, hey, we have a bunch of applications that are more or less stateless. We need to go deploy them into a separate site that has a different failure domain, right? A different physical failure domain. Fortunately, because we don't have to worry about the database, it's easy enough for us to go stamp out a second cluster in a separate failure domain. In this case, it was the same cloud provider, but a different region, right? So we were going from having a deployment in one region across a couple zones into having a multi-region deployment. And in their particular case, when we get into it a little bit more, there's actually opportunity that we could run an active-active deployment here with Istio pretty easily. But in this particular use case, they wanted an active-passive deployment. So what we want to do is be able to route around failures, right? So I know that I have duplicate instances here deployed. I want to be able to fail over between them independently, right? And I want to be able to fail over between my two units, A or B, independently. And this will be front end and back end in the demo, right? Just like before, we should be able to fail over in either direction, and also we should be able to fail over at the front door, right? So suppose, for example, that my client is resolving how it's going to talk to me via DNS. This cluster has an outage at the application layer. My clients are still going to be sticky to that cluster for quite a while, right? At a minimum, they're going to be sticky for their DNS cache duration. Chances are it's probably even longer. So I need the ability to also at the front door kick out requests over to the correct cluster as well. And so using Istio, we can do all of this pretty easily. And we can actually do these failovers between the backend instances that we're calling and bouncing around the front end in real time, right? So like in this demo, we'll actually sit down and we'll do this and we'll see it manifest, right? So we can affect change fast enough to react to a production event. Alrighty, so let's dive in. Just real quick, is this readable for the folks in the back of the room? Yes, cool. I'm seeing thumbs up. Great, excellent. Thank you. So just to set the context, as this is effectively our demo deployment, we have a primary cluster and we have a secondary cluster. In that cluster, we have two services. It's exactly the same in both. We have a front end and a back end. As with any Istio demo that you're going to see, notice that we have two containers running. That is the sidecar and the application itself. And of course, we have Istio itself deployed as well. I do want to call attention. We have one thing here that is not typical of a normal Istio deployment, and that is this core DNS instance here. I'm going to come back to that later and why we need that, but just note that we are doing some DNS stuff in the background, and I'll explain fully why. And if we go over to the secondary cluster, we can see that we have the same setup, and these are separate clusters. Notice these are different pod names, even though I got real worried the first time I tested it because I was like, that's 7D, what? It's the same pod? So we do have two separate clusters here. And similarly, the second cluster is also running Istio, also has core DNS deployed. Cool, so that is our setup. Front end, back end, two servers, two clusters. Let me go ahead and do a little bit of my setup here. These are our ingress IP addresses for the two clusters. So we're using Istio as our ingress proxy, right? We're going to use Istio's ingress gateway functionality. These IP addresses point to the ingress load balancers for our deployment. And so throughout, I'll use primary and secondary IP. And so if we hit our front-end server, we see that it echoes. Excellent. And we should see, whoops. And we should see the same here for the secondary. So I want to just call your attention to a couple things here first that provide context for the rest of the demo. So every time we make a request to any server in our demo, it will return the name, its own name, as part of the response. So notice when I curl, sorry, let me start there first. So I'm not using curl, I'm using a tool called HTTP. We could just as easily do the entire demo in curl. HTTP just has prettier output. When I use HTTP, just HTTP PI, HTTP is the name of the tool, sorry. This is the address that I'm calling. In this case, I'm calling the ingress IP address and the /echo endpoint. This is the header that I'm passing. Here I'm specifically saying, by the way, the host header, and this is because I don't have DNS with my setup, right? So I'm using raw IP addresses. I want a host name later. And so I'm setting a host name specifically in every request that I make. And what we echo, what we pipe into the command is the body of the request that the server will see. So in this case, hello DockerCon. Our test server also has one other endpoint that's going to be helpful for us, and that is a call endpoint. With this endpoint, whatever payload we pass as the body, the server will go just make an HTTP request to, right? So we have the world's least secure server. But here it is. What we see is, hey, we made a request to the front end primary server. It called never SSL for us. We got a 200, and there's the body that never SSL returned, right? So here's the body of the web page. Now we can call anything with it, which means, of course, we can call the services that are in our own Kubernetes cluster. And so this is how we'll actually see some traffic flow through our application. In fact, I can just go ahead and call the backend service. The backend is exactly the same as the front-end server. Every response that the backend server gives is going to have its own name in it, right? So here, the front-end server called the backend server on its default endpoint. And we see that we're staying inside of our single cluster, by the way, right? So I am calling the primary cluster's ingress. I hit the primary front-end server, which is the primary backend server. If I go over to the secondary cluster, we see exactly the same, right? Exactly what we expect. Secondary ingress calls secondary front-end server, which calls secondary backend. So let's go back to that DNS server. What I want to set up here, right, my end goal in this setup is that we're going to be able to route traffic across our clusters to these two services without the underlying application knowing. A key requirement there is that I need some uniform name across both of my clusters, right? So Kubernetes has this problem that names are scoped to the cluster and they're cluster local only, right? Names in Kubernetes do not span many clusters. If we're going to start to do routing across clusters, I need a name that spans across clusters. We'll use Istio to start to create these names. The problem is my applications need DNS to work, right? I'm going to use host names. I'm not going to hard code IP addresses. Up until now, Istio, Kubernetes is nice. It does this for you. I create a service in Kubernetes. It creates a DNS entry for me that resolves the cluster IP. Everything is happy. Istio has had this gap. In our deployment here, we have a core DNS plugin, which will process names that we create in Istio, and will publish them as DNS entries for us. And this is how we'll start to establish global names that we can use for routing. So I've already actually set this up with a name domain that will be ours, and it is the .global domain. And here I can show you. So because I'm in a GKE cluster specifically, core DNS is a little bit of a pain to work with. If you have a kube cluster that already has If you have a Kubernetes cluster that already has a core DNS server in it, you can just take the Istio plugin, run it beside your core DNS server, and get DNS names for service entries that you create in Istio. In this case, I have a separate set of servers deployed side by side. And here is the single important part. If we're using Kubernetes DNS servers, it's a little hard for us to resolve every single name, but instead we can very easily carve out a stub that we'll answer for. And so what this says is, hey, any request that ends in the .global, as opposed to like a .com or a .local, send it to my core DNS deployment, right? So right here is the IP address of our core DNS. We're just saying, hey, send request for .global to that. Sorry, I'm swapping back over to the primary cluster. So we have a DNS server that will mint names for Istio. They need to be .global, and this is how we're going to do routing across. So what does that actually look like? How do we start to do this? What we'll do is publish a service entry in Istio. And the service entry looks a little bit funny, but it looks something like this. Alrighty, so there's quite a few pieces here. First off, notice the host that our service entry claims or creates, right? That's the right way to think about it. In Istio, service entries create new names that are routable. So we're saying there's a frontend.default.global service that exists somewhere. We're saying it's HTTP, it's on port 80, sure. Here we mint a VIP for it. This is why the service entry is special. Typically, if you were going to use an address in a service entry, this would be an IP address or a VIP that you've already created. In this one, this is actually the DNS address that core DNS will return for us. And this is the way that the Istio core DNS integration works. And that address critically does not need to be routable, right? Istio doesn't care what IP address your application picks, because we're going to ignore it and we're going to do routing ourselves based on SNI, exactly like I said before, right? So I don't care what IP address your application uses, so we can return anything, including a non-routable 127 address. And here is where the magic actually happens. So we say, hey, this global service, this frontend.default.global, has two endpoints that I can address. The first one is the egress gateway. This is local to our cluster, right? So I can run an ingress. By the same token, I can run an egress proxy. And what's cool is that I can force traffic out that's heading out of my cluster through a specific egress point, which makes things like firewall rules pretty easy. And so we use that in this demo. It's not required for this cross-cluster setup, but it's a nice plus if you're, for example, doing things like whitelisting specific IP addresses for cross-cluster communication. And then the second piece is a little bit more interesting. This IP address here is, for those of you that don't have perfect recall, like me, because I would never remember this is our secondary IP address, right? So what this says is, hey, by the way, there is an endpoint for my front-end service. It exists in a different network, though. It's not the default network, it's an external network. That means I can't route it here, right? It's not reachable from my L3 network necessarily. But it's the remote ingress, it's the ingress to my remote cluster. And notice we have a magic port here, this 15443. This is an artifact of the Istio installation. So when we install this cross-cluster gateway setup, we designate a special port for the cross-cluster communication. So what this says is, when a request for frontend.default.local comes in my local cluster, send it to the egress gateway. The egress gateway behaves specially, and when it sees a request come in, it's going to look for external networks, and it's going to route a request that's coming in to the correct external network. So let's actually, and we have the same for the backend. And I want to stress that there's a decent little bit of complexity here, but this is one-time setup. So, and I'll talk a little bit towards the end about some alternate ways to do this that are even simpler, that aren't yet out. They're checked into master, but they're not yet out in an Istio release. But here we are. So I have my front end. I have an identical matching one for the back end as well. And we can see how this works by using this global name. Here, this is the first instance that we've seen of cross-cluster communication. I have my server in my primary cluster that called the backend in my secondary cluster. I had to change the name, right? I had to specifically call the global name. But I can see that the routing occurred successfully. Now, we have all the pieces in place. And again, I want to stress this would be one-time setup that you would do. Now, we can actually start to affect traffic shifting across these clusters. So, for example, suppose that my backend service goes down in my primary cluster, and I want to hit the emergency button and flip all my traffic over. This is exactly the active-passive use case that they were trying to solve, right? This is disaster recovery for specific services via failover to a remote cluster. What I would do is author a virtual service. So this is how Istio manipulates names, right? So this is, if there's something to take away from this talk, it is Istio routes based on names. You can use things to create names in Istio, and we're about to see how we can manipulate names to affect routing. This is the heart of how Istio networking configuration works. It's name-centric. So when I want to route all of the traffic from my local cluster over to the remote, I simply use the names. I say, hey, if you see a request for the local service for the backend in my default cluster, route it to the global one. And that's it. So we can take this, we can apply it. And now what we see, we'll go back to the normal application name, right? If we're in Kubernetes, I can just use the short name of the service. And we're routing, right? So with that, we can just seamlessly fall over. No application changes, doesn't matter, doesn't matter if you're using whatever version of the Kubernetes name you're using, doesn't matter. We can fail over without the application knowing. And critically, our secondary cluster wasn't affected. If I curl the secondary cluster, I see that we got the secondary front end and the secondary back end. No change here. So that's awesome. And it happens that fast, by the way. This was real time, right? Like this is, it's instantaneous. It's really neat. This core functionality is actually everything, like this one thing is everything that you need to know about how Istio networking works to actually affect traffic changes, right? There's other clauses that you can add in to decide when the rule applies or not. You can have match conditions. You can have a lot of complexity there. But the heart of it is this. It's names. And of course, we can also, at ingress, do that kickover of our front-end service, right? So in the case that my entire cluster has failed, I can go ahead and do the same general principle. This one looks a little bit different because we're doing it at ingress. So the previous rule that we had was applied at sidecars. This one applies only at our gateway, and we know this because it lists a gateway in the rule. Right? So here is the host that we've been using to communicate with the server every time, right? And what we say is, hey, when you see that host come in, send it to the global front-end instance. This is exactly the same as the backend, right? The only difference is I've attached it to my ingress gateway. And here what we see is even though I'm communicating with the primary IP address, the actual instance that I hit is in our secondary cluster. So what we just saw is that we hit the ingress of one cluster. It said, nope, I don't have instances of this service. Let me route you somewhere that does. Everything that I'm showing you here is, and so this is the meat of it, right? Let me see, are there any other particular things I want to show you? No, this is the big stuff. Again, just to recap, this is actually the topology that we had. Here are the key things that I want you to take away from this particular demo. Name-centric configuration model. Using DNS, we can create global names. If we're going to route across clusters, we need global names. If you're doing Kubernetes or you're migrating to Kubernetes, you're looking at this, one of the single best things that you can do now to prepare yourself for later is to establish a global naming scheme and start to use it consistently. We can affect traffic flow without the application knowing. And as a nice plus, we can do this via an egress proxy, which makes firewall rules a lot simpler. So we're pretty tight on time, and I want to get to some later content. So I'm not going to dive into this to how we might decompose a monolith, but I'll talk about the high-level strategy, and we won't go through the specific configuration, right? So I have my monolith A. I'm going to stick it behind an ingress proxy. It's probably already behind an F5 or something like that in your on-prem deployment. You know, we can put an Envoy there behind that F5 as well if you want. We're going to pick some slice of the functionality. We're going to pick some piece of the functionality to slice off, and we're going to make this our first microservice, right? This is how we start to break down the monolith. The key is we don't want our clients to know. We want to maintain the facade of the monolith so that we can do our backend changes without actually breaking our client behavior, right? In this particular case, this customer was in the process of doing a bunch of big backend migrations, but they had third-party callers, right? So they had a bunch of third-party people that were using their SDK. They can't break the SDK. We have to maintain the facade, but we need to rewrite the backend. So the key is that we can use Istio to emulate the facade of this monolith with Envoy. And we can do this with the virtual service and with the routing configuration there, such that all the normal requests flow into the monolith as before, but our new requests, we can pick the specific HTTP paths, if that's how we're decomposing it. We can pick the specific source subnets or other request features to decide that we're going to go over to the new one. What's pretty sweet about this, by the way, is that we also have a very fast path to fallback should something go wrong, right? So we saw how fast routing changes can be affected. We can do the same thing here, for example, to roll back from having deployed, from having sent traffic into our new instance to the old one. And even better, we can do things like start to upgrade the underlying transport protocols. And as long as Envoy can do the transcoding between the two, for example, gRPC it can, we can maintain our facade without changing, for our clients while we go wild in the backend with, gRPC or whatever thing we want. So again, I'm going to skip over this just for time. The key takeaways here, we can use Istio to maintain a consistent interface. And again, name-based configuration is the essential piece. I will have the code for the demos available after the talk so that you can go see the virtual services that would be part of this demo. And so the final thing that I wanted to do before we had just a couple minutes left, this was not in the outline, but this is maybe some of the better things that I can give you to walk away with, which is I've talked with a bunch of different companies that have attempted to adopt service mesh that have successfully, some that have not. And so I wanted to leave you with some of the common traits that I have seen of successful adopters of the mesh. The single biggest trait of people that have been able to successfully adopt a service mesh is that they didn't try to do the entire thing in one go. They had one thing that hurt, and they focused on that one problem, and they used the mesh to solve it, right? I've talked with companies that visibility, observability, is the thing that hurts most in their deployment, and they use a mesh to get visibility. And then later they see, hey, we have this mesh here. We can start to do other features. But visibility is the impetus for doing it. By the same token, encryption in transit is a common one. By the same token, resiliency is a very common reason. Don't just adopt a mesh because it's a cool thing. Don't adopt any technology because it's a cool thing. Adopt the technology because it solves a specific pain point that you have today. If you don't, you're probably not going to successfully adopt your whatever it is that you're trying to pick. A small group, by the way, most of these points are actually just generally true about any change in infrastructure or any change in your organization, full stop. They're not necessarily very service mesh specific. Any change in your organization, you're going to need a small group of champions. This should be the people that are experiencing the pain, right? So for a service mesh adoption, the team that is championing the service mesh needs to be the team that has the pain that they're trying to address. Otherwise, this is the skin in the game metric, right? I'm not motivated to go through the trouble of deploying this mesh when I'm not the one that has the problem. Typically, the most common case that we see is that it is some central team that drives the adoption of the mesh, a central observability, networking, or security team. This is the group that over time will become your experts in your organization for operating this thing, right? The core principle is to focus the pain of these areas onto a small group of experts. This becomes your first small group of experts, and they will be the team that is responsible for the piece of that pain. And over time, they'll onboard other teams to start to address the other areas of the mesh. Consistently, people that have successfully adopted Envoy-based service meshes have spent time learning Envoy. Often they do this in an ingress use case before you go to sidecars. A lot of times they'll not even use a control plane initially. They tend to only give a very small set of the service mesh configuration to any particular set of users, right? Most of that complexity that I showed you in this demo is not anything that an application developer ever has to see. The only piece of configuration that an application developer needs to see is that virtual service that was that little 5-line chunk of config that said, hey, send the local service to the remote one. That's all your application developers need to see. Hide the complexity from them. They don't need to see it. Give them the smallest piece that solves the pain that they have. And later you can add more. And the final thing to remember is you're in it for the long haul. This is not it's not an immediate thing, right? It's not a one-day thing. It's not a one-quarter thing. It is a continuous process. And the most important part of that process is actually the education across the organization. With that, Lee Calcote and I, Lee Calcote is a Docker captain. He may or may not be here in the room. He and I are working on a book together. There's already an early release out. And it'll be published later this year. There's quite a good bit here around how Istio works and how a lot of the configuration manifests, how to go debug pieces. Hopefully this will be a valuable book for people that are actually trying to use the thing to understand the system, understand how it fails, and go forward. So with that, we are out of time. So I'll be up here to take questions afterwards. Thank you for coming. Thanks for paying attention.